So back to the gradient function, how we're finding the slope of a tangent to a curve. We saw how we could do it for lines and semicircles, but that was very limiting. We want to be able to do it to any curve. So here's a random curve. If I want to find the slope of that tangent at the point P, we said we could estimate it using a secant. Now this time with my secant, I haven't gone a point either side of P. I've actually included P as one of the points. But it's still going to give me an estimate. Again, is it a grade estimate? Well, the one I've drawn there, probably no. But it is an estimate. So the question then is, if I'm going to use P as one of the points, where would the best spot be to put Q to get the best estimate? Now, if you imagine sliding Q down the curve, what would happen to that line? As we go down, it's going to get shallower and shallower and shallower and closer to that slope. Ideally, we want it as close to P as possible. In fact, ideally, we'd like it to be the same point, but of course it can't be the same point. All right, just have a look. There's P and Q. We're saying we're getting it as close as possible. So P would have some coordinates, x, and the y value of function x. Q, I'm going to add on something, so x plus h. I could find the slope of PQ, and it would end up being function x plus h minus function x over h. Now this is where limits comes in handy. Because what we're saying is, look, yes, we know it can't be the same point, but I want to know what's happening to the slope of that as that point is getting closer and closer and closer to P. In fact, as soon as that distance is 0, what's happening to that limit as it's approaching 0? Because that then will tell me the exact value that I want. So the slope of the tangent will be that slope that we just worked out. Function x plus h minus function x over h, but the limit as that h approaches 0. That is what we call the derivative. The derivative of y with respect to x. How is y changing as x is changing? Symbols, dy dx. Now where did that one come from? I'm not 100% sure, but I think it's from, originally they might have used the Greek letter delta, because delta often represents change, and then it's become d over the years, so dy dx. Sometimes y with a dash, like we saw with the gradient function, it was f dash x. Sometimes just y with a dash. And as I said, well, f dash x, of course, we could use that one as well. And sometimes we simply, instead of writing y, write what the actual function is. So I'm going to differentiate this function with respect to x. There are all different ways of writing the derivative. And our derivative simply measures the rate of change of something. Slope is the rate of change of y with respect to x. So there now is our formula for the gradient function. All I've really done is replace the words slope of tangent and then gradient function, because that's what the gradient function measures, the slope of the tangent. This idea is called differentiating from first principles. Now there's a lot of things that have first principles. All first principles really means is the first idea. Differentiating from the first idea, and this idea of finding the slope of a secant is the first idea with the calculus. Let's use the formula with something where we know what the answer is going to be. So I've just got a straight line there, because we know the slope of that's 6. So I should get an answer of 6. Function x then is 6x plus 1. I'm going to need function x plus h. Everywhere I see x, I'll replace it with x plus h. So my derivative, I've used dy dx. The limit as h approaches 0, and then when I substitute in, there's the expression. But there's a bit of cancelling. And what we find is everything on the top of the fraction that doesn't have a factor of h goes away. I end up with 6h on h, and now I can use the idea of factorise and cancel. Well, I don't have to factorise 6h, obviously it's one term, but there we have it. What's the limit as h approaches 0 of 6? Well, it doesn't matter. In this case, h is approaching 0. 6 is always 6. And we know the answer to that is 6. Have a look at my setting out. You write the limit as h approaches 0 on every line until you actually substitute in. So I'm still saying limit as h approaches 0, limit as h approaches 0. When I finally do substitute in, oh, okay, that's 6. Well, let's find the equation of the tangent to this parabola. X squared minus 5x plus 2 at the point 1, negative 2. Function x, I'm going to need function x plus h. All right. Substitute it into our formula. And again, we should find all these terms cancelling, leaving me with 2xh plus h squared minus 5h. Everything's got a factor of h in there. So that will cancel down nicely. 2x plus h minus 5. I want to know what's that doing as h approaches 0. Substitute in, and I have my answer. 2x minus 5. That is the gradient function. It's not actually the slope of that tangent yet. We now have to substitute the point we're interested in looking at. So when x equals 1, that turns out to be negative 3. I now know then the slope of the tangent is negative 3. When you're writing out your solutions, put all these things in, explain what you're doing. So I said I'm going to substitute in x equals 1. I found it's negative 3. My interpretation of that is, okay, the slope of the tangent is negative 3. We'll put it into our point slope formula then, and we can eventually get the equation of our line. There it is. Y equals negative 3x plus 1. 9b we'll add.